All right. Well, we're going to talk about today. Welcome back, and we're going to talk about the washer method and how to use the washer method um, to find out the volume of a solid when it's revolved around a certain axis. Now, you might be wondering, what is the washer method? Well, if you watched my previous videos, um, what we have is a um, area, a region that's going to be revolved around a certain axis. Now, whenever we want to find volumes, the key thing to find a volume is we really are just using one equation. To find the volume of any solid, you need to have, you need to integrate from A to B. You need to find the area, okay? The area of our cross section, so that's the area of a cross section. And you're going to multiply that by obviously dx, which actually is the width, which helps you give volume. Okay, and you take the volume from A to B, and we're just going to add up all these small little volumes together. So in here, when we're revolving something, we're actually, what cross section are we using? Well, if you're revolving, it's going around in a circular fashion. So what we're using are discs or circles. And so our equations that we're using are actually pi r squared. We're looking for r, which are a circle. Now, in previous ones, we've had discs and we found this out. Well, we're going to revolve this around the x-axis. So here's our x-axis, and we're going to be revolving around r, okay, this region r, around the x-axis, okay? And so when we do this, it's going woo, woo, woo. And so this value, what's happening is really it's kind of being reflected over here. And I'm going to have another one going like this. And what we have then are two, all right, values right here. And we're placing discs around this different parts. Okay, so if you kind of think about this, we're placing huge discs around here, and so we're rotating this around. And so we have some other discs right here, rotating around. But you see that we have is some solids here, but you see that there is some space in between. And because there's a space in between, our solid right here is actually, we have the solid portion going like right here, but then we have a hole in it. And when you think about a circle with another circular hole in it, we refer to this as a washer, or sometimes you can know it as a icing donut method, all right, the donut method. And so to do this, we're actually thinking about, all right, how do we revolve this? Well, how do we take out the whole? Well, we're actually going to take out and subtract, all right, the larger circle from the smaller circle. So we have is a big R and we have a small r. And so the key thing is we have to know where's our axis of rotation. And so this case, we're talking about the x-axis. And then we need to figure out, okay, what is the largest value that we're finding? So right here, we're actually going to take this and we're going to find from this x-axis, or from the axis of rotation, our big R is from the axis of rotation to the farthest point in this. And actually, this is what to refer to as big R, not the R region, but this is our big radius. Okay. And so to find this radius length, we're going to integrate this from A. Now, if you watch my previous video, I have this right here, and I found the intersection. And our intersection is at 0.2387. So 0.2387. We found this by finding the intersection between these two different values. Okay, so we have the square root of x, which is located right here. All right, and that is going to be our farthest point. And so we're going to go from here to 1. And so our big R, our big radius, is going from here, which is the square root of x, to this point, which we're going to subtract 0. So that's our big R. Our smaller r, okay, is the value we're taking out. And so what is that? Well, we're taking out all of the value below this into this point. So we're going to call this just little r. Okay. Now little r, it goes from here, this point, which actually is that equation. So we're going to take e to the negative 3x minus this point right here, which is on the 0. And so that is our little r, little r. Now on both these, we are using circles. So our first circle is going to be big R, so our bigger value, all right, minus our little circle. And so when we're writing this out, all right, I'm going to have pi big R squared, in terms of x, okay? And so it's going to be pi times the square root of x squared minus, all right, pi times little r squared right there. I'll put the parentheses around there so we know that taking the whole thing squared. And so we have here is going to be pi times little r squared, which is going to be e to the negative 3x, that quantity, squared, and then dx. Now, what do you notice when we have this? Well, each one of these is going to have pi. We're going to be taking that out. And so what we have is pi out here. We have 0.2387 is our one intersection. And then we're going to go to the farthest point, which is right here, which is 1. And we really can just take this, we can square, so we have x minus, and when we have this, we can multiply by the exponents together, so we have e to the negative 6x dx, and that would be our value. We can go to our calculator, and if we wanted to find that value out, there we go. And we're going to go to our go to math, and we'll go down to 9, which is our function integrate. All right, now I clear that, so I can quit. Make sure we get out of here. I have my other equation in there before. So we can go to pi. I'm just going to write this out. Pi, go to math. We're going to function integrate 9. We'll go to a lower value, 0.2387. We can go to the upper bound, which is 1. And then we're going to put in our 1, because square root of x squared is going to be x minus, all right, we have our other value, which is going to be minus e, all right, raised to the negative 6x power. And then we have x right there. And we can find out what this value is going to be. And we can see that that value right there is going to be 27 or 25 point. 25.264, and we'll 1 around that. That's what we have there. All right, pretty cool, huh? I'm going to get rid of that now. Now let's see what happens, and I'm going to erase this because I think hopefully we get the point of what we're doing here. Well, what happens if we change our x rotation? So let's say we go up and do at 1. Okay, let's say we go to 1. And I'll make this in green just so we can see it right here. So we're going to go 1. Now we're going to rotate this around here. So we're essentially doing the same thing, but now it's going to be up on this top portion right there. So we have a mirrored image going like this, and we're still rotating, but we're rotating it around this way, okay? Going around there. Okay, so what happens here? Well, we're still integrating this way, and so we have the same value, but what you notice is that our big R changes because from this x rotation to the farthest point down is actually going to this curve right here. Okay, we're actually going to that curve. And so this is our big R of our radius. So what is that length? Well, if we start here, we always start top minus bottom. And so really you're taking 1 minus this value, which actually is our E. So it's going to be e to the negative 3x power. So that's our big R. Our little r is from this x rotation down to the part where there is a gap there. That's our little r, smaller of the circles, and that's going to be kind of right here. And so what's that going to be? Well, top 1 minus this equation, which is a square root of x. And so that's what little r is. And so when we write this, we're going to have the same ellipse integration because we're still integrating from here to 1, so 0.2387 to 1. But now we have a different function. So now we're going to have 1 minus e to the negative 3 x, that quantity squared, because that's our radius, minus then our little r, which in this case is 1 minus the square root of x squared. And then we're going to put our dx there because that's our width. And there we have it. We can go to our calculator and figure this out, but that is our new value. Okay? And so when you have axis rotation, it's really important that you draw this out. And what I like to do is draw in my different radii. Okay, we're going to try one more. If you want to try this out to see what it is before I go through it, please go do that. And so I'm just going to erase all this other stuff here because it's going to change some things. And I'll just take this part and move it right here, and I'll delete that. And so now this next one, we're going at -2. Now, -2 you can't see here, so we'll go and I'll take and put this in purple. And so -2 is going to be somewhere down here. So I'll just say probably a little bit lower than that, but I'm running out of room. So I'll just say this is going to be y equals -2. Okay. Now y equals -2. What is changing here? Well, we're still integrating it from our still same limits. But what do you notice is our big R? Well, big R, we started at axis of rotation. We go to the farthest point, and if you notice, our farthest point is once again back to this curve, which is, all right, the square root of x. So big R is going to equal, all right, top, the square root of x, minus the bottom, which is -2, so it'll be +2. And that's what our big R value is. So that's our big radius. Our little r, because you notice that we have this big gap now between, because we're rotating this around, and we're now creating this huge gap in middle, okay? If you can kind of think about that. So we have this huge gap over here. And so what is this going to look like? Well, right here, our little r going from here, okay, all the way down to our axis of rotation, because this is where we're rotating around that line. And so what is that little r going to equal? Well, top, that's going to be e to the -3x minus the x rotation, which in this case is -2, so it'll be +2. And that's our little r. So how do we write this out? Well, we have two circles, so we're going to put pi because we factor that out. We're still going from -2.387 to 1. Now our big R is different, so this one's going to equal square root of x plus 2. We're going to square that because it's a circle. Minus our big old hole, which is our little r, smaller hole, which is in this case going to be e to the -3x plus 2, and we're going to square it with the dx. And we can put it in our calculator to figure out those values. All right. And so that is how we can use what is known as a washer method. The washer method is where we're taking a bigger circle and subtracting out a smaller circle because there's holes in it, and it's creating a washer. Once again, because we're revolving around different axes, either the x, or we had a 1 or even 2 here, we're using cross sections with our circles, and we're having two circles, and we have to figure out what the largest circle is. The largest circle is from the x rotation down to the farthest function, and we find that length by taking upper minus lower, and writing that out, and then putting it into our integral. Well, I hope this helps you out in understanding how to use washer method in order to find the volumes of solids. All right, well, good luck and good bless in the rest of your problems.